This is Algebra 3. It's a lesson on limits. This is part of our sequences and series unit. And so we need to know what limits are once we get to infinite series. So this is just kind of an intro overview. What a limit is it's basically just plugging in numbers that get increasingly close to whatever x is approaching. So we say that this right here, it really says the limit as x approaches infinity. And so, I mean, you could tell that if we plugged in increasingly large numbers, like, say, 5, which is not large, but we start there, we'd get 1/5, and that's like 0.2. You plugged in, like, 50, that would be 1 over 50, which would be like 0.02. And then if you keep on plugging in larger numbers, we can kind of tell what's going to happen. We're going to get closer and closer and closer to 0. We're getting smaller and smaller decimals. So presumably, if we kept on doing this forever, the numbers that you'd plug in for x would be super large, and our answer, our fraction that we'd get out of it, would approach 0. So the limit as x approaches infinity of 1 over x is basically 0. And we can't ever get to infinity because infinity is not a number. It's just the idea of increasingly large numbers. Same thing would happen with negative infinity down here. You're just going to get negative 1/5, negative 1/50th, and then you're still getting closer and closer to 0 just from the negative side. So here's an example down here that basically says, all right, if you had some kind of sequence, 9/5, 16/4, 65, 27ths, and then that's basically the general formula, 7n squared plus 2 over 2n squared plus 3n. If you started plugging in increasingly large numbers, we can see what happens. Like the 50th term in this sequence is right here, and it ends up being about 3.398. The 100th term is 3.44, then 3.489, and you can plug this in and verify yourself, but we're just doing it for you. So it says basically we kind of figure out that as n approaches infinity, the value appears to get closer and closer to 3.5. Like if we plugged in 1,000,000, we're going to get even closer to 3.5. So basically we know that the limit, it converges, it's said to converge to 3.5. So that's essentially what a limit is. We want to know what happens as we put in increasingly large numbers for our variable. So we can go one step farther and basically say, well, what if that x on the bottom had some kind of an exponent? So if we know that the r is greater than 0, it's basically going to make the number on the bottom bigger, right? If you have any exponent, like 1 over 2 to the 3, let's say, we plugged in 2 for x as x approaches infinity, so we're at the small end. We're not at big numbers yet, but still this is going to make it 1/8, whereas if it didn't have an exponent, you just have 1/2, it'd be 1/2. So as x approaches infinity, when you start plugging in increasingly large numbers for x, whatever r is, as long as it's like, a positive number, it's just going to go to infinity. It's going to go to 0 much faster, your answer will be. Because you could plug in 1 over 100, but then, if you have some exponent r, let's say maybe it's 2 in this case, then it's still just going to be a larger number on the bottom even though you only plugged in 100. So it's going to end up going to infinity, or to 0 even faster. So in general, if you have an exponent with r and it's connected to a variable that's on the bottom, your number's going to 0 very fast. Your function is. So either way, these are going to 0. Next is really basically from the book. It just shows a whole bunch of theorems for limits, and none of this is really, it's not a big deal. This isn't like the log properties where we actually needed to memorize everything. The limits all do the same thing. Basically, if you have a limit of, a and b, a plus b, you can split it up into 2 separate limits, the limit of a plus the limit of b. That's what this one says. Same thing with subtraction. Multiplication is the same thing. If you have the multiplication of 2 separate things, you could split them up into 2 separate limits and then evaluate. Same thing with division. So don't worry too much about that. Just it's a general rule. We can split up limits. All right, so here's an example. We're going to mess around with this guy for a little bit. Basically, we want to see that, let's just evaluate this for like 50. 50 is not close to infinity, obviously. It's a number we can even count to, but it is larger than 1, let's say. So if we plugged in 50, it's 3 times 50 plus 5, and then you get 50 minus 4 on the bottom. This is 155 over 46. And if you use a calculator, you get about 3.37, let's say. I rounded a little bit. Now let's jump a little bit farther. Well, maybe 100. How about? Let's do 100. 3 times 100 plus 5 over 100 minus 4. This would be 305 divided by 96. And this ends up being 3.18 about. I rounded again. So we can see that we're still above 3, but we're getting closer to 3, and not 3.3. Now we're at 3.1. If we plugged in, let's get really crazy, and let's plug in like a million. And I'm just going to write it out. I don't want to write out all those numbers. We're going to plug in a mil. So this is now mil minus 4. And do this on your calculator. Don't mess around. So you end up with 3,005,000 over 999,996, which if you divide that, you get 3.000017. So as we can see, the larger the numbers we put in, we're getting closer and closer to 3. All right, so this is a crazy problem. I mean, instead of actually plugging in all of our numbers, we do have different methods. And we'll learn about this method in a couple days as well, but just to expose you to it right now. Basically, we see that all these variables, if we were to plug in some really large number, and notice we're talking about as x approaches negative infinity here. So we're plugging in larger and larger numbers that are negative. But if we were to do that, I mean, we're going to get some really just messy stuff. Like it's going to be all kinds of, computations. So let's just not do it. So what we can do is we can divide each term in the numerator and denominator by the highest power of x. So what I mean is we're going to divide every term, like x to the 4th has the highest degree. So we're going to divide every single term by x to the 4th. So what this looks like is 4x to the 4th divided by x to the 4th plus 3x squared divided by x to the 4th plus 9 divided by x to the 4th. Over 8x to the 3rd divided by x to the 4th, and so on. And then we also have this plus 1 over here. It's not really part of the limit. It's just we're saying whatever this limit thing is, then plus 1. So the interesting thing about this is we can simplify a lot of this stuff. We're going to say that, the x to the 4th over x to the 4th, those cancel out. X squared on top and x to the 4th on bottom leaves an x squared on bottom. 9 and x to the 4th over here, nothing happens to. 3 of these x's and 3 of those x's are gone, so I'm just left with 1 x on the bottom. Both of these guys kill each other. And then you have 1 over x to the 4th left. So just as we did before, I mean, if we're still going to be plugging in numbers that get closer and closer to negative infinity. So these are like really big numbers. And so anytime you plug in a really big number that's on the bottom of a fraction, we know that that piece of the fraction is converging to 0, just like we showed on the very first example of this video. So what we want to think about is that which of these terms in this fraction are going to be 0 and thus pretty much irrelevant. Like right now we have 4, that's by itself, plus this term 3 over x squared. You're going to plug in larger and larger numbers for x, and then you're squaring them. So 3 divided by a really large number essentially converges to 0. Same thing here, 9 divided by some number raised to the 4th eventually converges to 0. On the bottom, 8 over x. X is going to get really big as well. 8's not that big. 8 divided by a really big number is going to turn into 0. Minus 7, the x's canceled out, so there's nothing happening there. but then also minus 0. And then later on we have this plus 1. So really what happened is that instead of actually computing this and plugging in really, really large numbers, you have 4 plus 0 on top, and then a negative 7 on bottom. So that looks like negative 4/7 plus 1, and then we can compute that. That's 3/7. So that's what this limit turned into. And it makes it a lot easier on us when we can just eliminate terms that are going to converge to 0 because we're plugging in really large numbers. And then we end up with just a very simple fraction, and then you just add 1 to it. So this is kind of a nice method to get rid of unnecessary terms and also not have to compute or evaluate large numbers in a function. All right, this is probably the last example. So we want to do the exact same thing that happened before. Any term, we want to divide all terms by a variable that has the highest exponent. So the highest degree variable, everything's going to get divided by. That looks like n to the 4th over n to the 4th, because n to the 4th is the highest degree, plus n over n to the 4th over 3 over n to the 4th minus n to the 3rd over n to the 4th. This is the limit as n approaches infinity. So we're plugging in really, really big numbers. But we can simplify this to look like the limit of n approaching infinity of n over 4, n to the 4th ends up being a 1 plus n and n to the 4th ends up being 1 over n to the 3rd. The bottom stays as it is, n to the 4th, and then minus 1 over n. These all cancel out except for 1n on the bottom. So the same thing's going to happen here. Any term that has an n on the bottom of a fraction that's still there is going to say that it's converging to 0. So essentially, this term is going to be 0, this term is going to be a 0, and this term is going to be a 0, which should mess with everyone and make you feel gross, because right now we have 1. You end up having 1 over 0. And again, we're talking about numbers that are approaching infinity. So this number down here wasn't getting to be 0. It was, it was approaching 0. So in the opposite sense, if we have any number on top, and then the denominator is getting to be a very small number, that's going to end up making our function grow without bound. Like if we, you could just make an example. 1 divided by 0.01 ends up being a bigger number. If you plug in 1 divided by 0.000000001, you're going to get an even bigger number. So essentially, just as before, if the denominator increases really large, it gets to be really large, our overall number gets to be very small. But if the denominator gets to be very small, our overall number gets very big. So the smaller that the denominator gets, like if you could possibly plug in 0 on the denominator, we would say that this goes to infinity. So this does not have a limit. So you should be able to attempt day 7 now, where you can at least try to divide each term by the variable that has the largest exponent, and then see what you end up for a limit. Good luck.